Last time we kind of went over what the definition of a Lie algebra is, and we kind of roughly covered, we covered like the concepts of the adjoint representation and derivation, and we kind of roughly covered the idea of the ideals. Morphisms. Today we're going to be looking at ideals and maybe going to be taking a bit of a closer look at what morphisms, how more details of how they work. So yeah. The first topic here is going to be ideals. So if you've ever taken a abstract algebra course before, you may remember ideals from ring theory, where in a ring, an ideal is a subalgebra, essentially, a subring, I guess, in that context, which not only closed under addition and multiplication, but it's also closed under multiplication by arbitrary multiplication of like the parent ring. And we have a similar idea here in the context of Lie algebras. So a subalgebra, we're going to call it K inside of our main Lie algebra L. Is an ideal if its image, if it is stable under every inner derivation. We're going to go over that in a second. Of L. So what does this mean? If you remember from last time, an inner derivation is just the same thing as the adjoint representation of some element from L. So what this is saying is, for every element x inside L, we have that the adjoint representation of x in the context of L, working on the entirety of this set K, is still inside of K. You can't leave K through adjoint representations, even if they're coming from like the parent element, the parent algebra, and not the ideal itself, which is the same kind of construction as what we saw before in ring theory, and just in this new context. And we can write this, keep in mind, this just means like this. And keep in mind, by anti-symmetry, keep in mind this this Lie bracket has to be the negative of swapping the order of the elements, and because K is an algebra in and of itself, it has to be has to contain additive, like the additive inverse of elements. So we have that left ideals are right ideals. So there's no need to like in ring theory, you kind of have like ideals from one side or whatever. Because of all the symmetry we have with the Lie algebras, we can just go ahead with just ideals in general, as you can see. And sometimes we notice here we specify that it's closed under inner derivations. We can have if K is stable under all derivations of L, it is called a characteristic ideal of L. Because keep in mind, remember, a derivation is just a map on L which is stable under, which kind of splits across the product, sorry. And we have that all of our adjoint representations are derivations, but they're not necessarily all of the derivations we can find. So I guess the next thing we need to look at is kind of look at how ideals relate with one another. So we're going to keep using, let sorry, I'm gonna pick my letters here. Let L be a Lie algebra. K an ideal of L, and M a characteristic ideal of K. Then M is an ideal of L. And this is given, okay, and there's also a caveat which if this ideal here is a characteristic ideal, then this idealness here is also characteristic. So, and the proof they give here is every inner derivation of G let D be an inner derivation of L, then D has to leave K stable, and then we can just take the restriction of that derivation on K is a derivation not necessarily inner. K leaving L stable. And of course, we can, in this other case where these asterisks are characteristic ideals, we can get rid of this inner here, and we have a proof for the case of characteristic ideals. Now we'll look here if K and M, that is a terrible M, are ideals of really the same, the algebra, we'll call it L, then there's some, and keep in mind this is like every element that can be expressed as a sum of an element of K and an element of M, and their intersection are also ideals of L, of course. And so another little note here is we often look at like what looks like the Lie bracket of these two ideals here. I guess this can be over submodules. I'll write it for ideals, but it generalizes to submodules, obviously. And this is just elements. This is just the set. The Lie bracket of these sets is just the set of the Lie brackets, as you'd expect. Similar to the sum and intersection we saw there before. And we can write similar for the bracket of a subalgebra and an element, like that. And this generated set here is an ideal if K and M are also ideals. I guess we should prove that. Sorry, there's always yelling upstairs. I thought it'd be quieter down here, but okay. And so the proof of that, well, once again, let D be an inner derivation so then we can just see that that D acting on Km is going to be dk comma m plus k comma dm, which is going to be inside, because this is still an element of k and this is still an element of m, so both of these terms are going to be inside k bracket m. And a couple more constructions here we're going to write out. If n is kind of an awkward term, whatever. N inside L is a submodule then we have that the normalizer of n in L is the set, which we write like this. It's going to be x in L such that the bracket of x and on n is inside n still. And this is going to be a subalgebra. If n is an ideal of L, if n is a subalgebra of L, of course, its normalizer is an ideal. Alright, and so that is a start. Whoops. Sorry, there's two different buttons on my pencil. One of them scrolls the page down, one of them does nothing, and I keep getting them mixed up here. It's going to be a bit disorganized here as we go on, but we have 0 and L as the kind of, maybe trivial is going to be a bit too technical a word to use, obvious ideals of L. And we can kind of go through some examples here. We also have the center of L, which we define as the elements of L such that its bracket with everything is 0 in L. This is also an ideal. And this is one that's going to come up. This is an important example. This is going to come up later on when we start talking about series in a algebra. And if you recall from before, if the algebra L is abelian if the bracket is always 0, because it's derived from an algebra using that formula xy minus yx. So if the algebra it's derived from is abelian, that formula gives you a bracket which is always 0. So we have that L is abelian if and only if its center is just itself, which is basically just two different ways of writing down the same idea. which is that the bracket is always 0. We also have the derived algebra. Another one which is going to come up when we talk about series. And this is, you can tell what this is from the notation as we saw from before. Oops. Which is just elements which can be written as the bracket between two elements of L. And this is itself an ideal, of course. Alrighty. I'm sorry, I'm kind of bouncing between, like I said, a few texts, so it takes me a while to kind of scan through what we've already covered and what we haven't. So, if a Lie algebra L has only the two obvious choices as ideals, which essentially we're saying if the only ideals of L are 0 and L, and there's no other ideals of L, then we say that L is simple. And if you think about the one-dimensional case, everything is collinear with itself, so by alternativity, the bracket is always 0. So we often impose the condition that the bracket of L with itself, the derived algebra as we saw above, is non-zero. To avoid just the trivial cases we can get. And so then we see that pretty obviously the center of L has to be 0, and that the derived algebra has to be the algebra itself when L is simple. So just to go back once again to an example that we're going to be working with, as I said before, an example we're going to be working with a fair bit. Let us look at the case where L is the special linear Lie algebra on a field which is not of characteristic 2. Characters, yeah. Remember that the basis of L, and we're going to give names to these things. We're going to have X to our first matrix here, Y to the second off-diagonal matrix, and H as this one. And the bracket, of course, the bracket of two elements is xy minus yx as usual. And we can reduce this down because this is a basis, so we just need to look at how it works for every pair of distinct basis elements, as we saw before. So the bracket of x and y is going to give us h. The bracket of h and x is going to give us 2x. And the bracket of y and h is going to give us 2y. And we notice that, because keep in mind that all of our adjoint representations are going to be linear functions on this essentially three-dimensional space. So they're all going to be 3 by 3 vectors, our adjoint representations. And so we see that the adjoint representation of H as a matrix, we often talk about adjoint representations as matrices. As eigenvectors of all three of these elements, x, y, and h, and they have eigenvalues. Well, the bracket of h and x is 2x, so that has a eigenvalue of 2. The bracket of h and y is negative 2y by anti-symmetry, so that has an eigenvalue of negative 2. And the bracket of h with itself has an is 0 trivially, so that has an eigenvalue of 0. And yeah, we're in characteristic not 2, so these are all distinct. So we're going to move a new page. Kind of awkward here, but so we're going to let I be a non-zero ideal of SL2 of F. Because it's non-zero, we can take a non-zero element from I of the form AX plus BY plus CH from I. Then the adjoint of X on AX plus BY plus CH is going to give us, recall, bracket of x and x is going to be 0, so our first term is going to be 0. The bracket of x and y is h. So this is going to give us bh. And the bracket of x and h is going to give us negative 2x. So it's negative 2cx. And so then we can apply a second copy of this. And so this is going to be the bracket of x on bh minus 2cx. Of course, x cancels out with itself. That just gives us the bracket of x with h, which is minus 2x times b, so that's minus 2bx. And if I'm not going to go through this again, but you can see that applying the adjoint representation of y twice to this element we have here is negative 2ay. Thus, if, say, a is non-zero, this ideal contains, well, has to contain an element of y. And similarly, if this is b, this has to be x, because ideal has to be by definition closed under the adjoint representations, because those are the inner derivations. And so because we have this element ax plus by plus ch, we have to have what its image is under adjoints, and so it has to have, we have to have y or x respectively in there. And so I has to equal L, because let's say, for example, A is non-zero. If A is non-zero, that means we have an element of X in there, which means from this closed under derivations we can get Y, and then it has to be closed in a bracket again, so the bracket of X and Y gives us H. And similarly, kind of the other way, in the other case, if A and B are 0, then we have CH in I non-zero. So H is an I because it has to be closed under scalar multiplication. And so once again we can go through the similar process here to reconstruct the other elements and get that I equals L. Thus we have that SL2 of F is simple, because if you can find any if you have an ideal that has any non-zero elements, so any ideal that isn't just 0, we can go through these adjoint, we can go through the closure under edit representations to get every other element of the ideal. So the only possible ideals are 0 or just everything. Oof. Alright, so what is next? So if L is a Lie algebra, I don't know if I should be capitalizing Lie here. Yeah, it looks like they do in the book. With an ideal I, we can construct the quotient algebra L over I, and that the construction should be familiar to you. It's the same as like the quotient group or quotient ring or anything that you've normally seen. With the, and this is an algebra to go through the this is a vector space. You can hear my family on upstairs. You hope, maybe, hopefully not. By the quotient of vector spaces. And there's also an algebra by our bracket of x plus I, y plus I is equal to the bracket of x and y plus I. Because keep in mind that's how quotients work, right? You're partitioning the space into equivalence classes, where each equivalence class is essentially a copy of the, in this case, the ideal. And so this is what our bracket is going to be. And of course, the question you always have with this is, this kind of case, to make sure that the quotient makes sense, is this unambiguous? Because that's the problem, is that the bracket in this case, we need to make sure that the bracket works the same across any representation, any representative of the equivalence class. So if we have that x plus I equals x prime plus I, and y plus I equals y prime plus I, so these are two different representatives essentially from the same class. Then we can alternatively write this as x prime equals x plus u, and y prime equals y plus v, with u and v coming from our ideal. Then we have that, and so we have two arbitrary representatives of our equivalence class. We have that the bracket of x prime and y prime equals, we can split across the we can essentially FOIL this because it's bilinear. And so we can write this as the bracket of x and y. And so we're gonna FOIL this out here. And so we get these three additional terms here, but we see that they all include elements from our ideal. And so this whole big term we have along down here is going to be residing in I. Which means that we have that this bracket plus I, so in this equivalence class, is going to equal to our original, and so we have that the bracket is going to work the same along the equivalence class. They go over the normalizer again, and then they go over the centralizer. Okay. We can write the normalizer of sorry. K and L as the normalizer L of K. And just a quick reminder, this is X in L such that the bracket of X and K is 0. I think I wrote this with the adjoint last time. That's alright. And we can define the centralizer, similar construction, as C L of K, and this can be defined to be equal oh, okay, sorry, I did make a mistake here. This just has to be, the normalizer just has to be inside K. The centralizer has to be 0. We have that the centralizer is a subalgebra of L, and how long has it been? That's one thing. I don't have like a great way to tell how long it's been with my current setup, but it looks like it's been about 45 minutes. Not quite, but this is such like a natural stopping point that I think I'm just going to keep talking here, kind of stall for a little bit, and then next time we will go through homomorphisms and representations, it looks like. Because I'm starting to get kind of a feel for like how many pages of book we can get through in a day, at least with our current spacing in that. And so yeah, I guess right here, next time we're going to be looking at morphisms, which we did look at before, but we're going to look at it better this time, and representations, And morphisms, yeah. Morphisms, representations, and morphisms. Sounds like a healthy selection of topics. And that will be in a bit. I'm gonna record some, yeah, I shouldn't talk about that here. Yeah, thanks for watching.